Alright, so now we're going to talk a little bit more about what design is and what the rest of the semester will look like. The first thing I want to mention, though, is that not all engineering design looks the same, right? Um, to start off, the very typical thing that we consider to be design um, is something that I'll call original design. Original design. Now, with original design, you're creating original concepts to address a need. So also, because it's original, right, and something like this doesn't exist at all, it typically involves invention. Like I said, this is the fun thing that we typically think of when we think of original design, or when we think of engineering design in general, right? Um, the Another type of design is called adaptive design. For this, we are adapting a known solution to a different but related need, right? Um, as you might expect, this process here of adapting a known solution to a different but related need actually happens quite a bit more often than original design. Right? Original design is quite difficult. Adaptive design is a little bit easier. A little bit easier than adaptive design is something that we call redesign. Right? You're improving on an existing design. Um, you know, you're going to incorporate user, new information on the user experience. Because you were so quick to get to the point where you're manufacturing it, you might redesign for manufacturability to maybe cut your costs there, right? Assembly is a big thing now. Can we redesign so that we can assemble it with robots as opposed to requiring people? In general, you almost always want to redesign for fewer parts, cheaper materials, and easier to assemble. And easier to manufacture. So yeah, you might also add some features. Maybe give it a new look. But for the most part, the design is the same as it was before. You're just changing some parts of it. New look. That's redesign, right? And finally, there's also something we call selection design. You're selecting components that meet performance, cost, quality requirements. But importantly, you're choosing these from a manufacturer's catalog. So, as you might expect, as we go in this direction, right? Actually, let's do that. Let's do that in red. Oops. Let's do that in red. I like red better. So as we go in this direction, right, as we move from selection design to redesign, we get more complex, right? The number of variables that you have to deal with selection design is really the number of possible components that there are out there. How many manufacturers are there? How many different models do they make? Done, right? That's not to say selection design is easy. It is not. It is not easy. But there are less variables than there are when you're saying redesign, right? And with redesign, though, you're leaving your design mostly the same. So it's actually a little bit less complex than adaptive design, right? Where you're changing a design to meet a new and different need, right? Here you know your need for the most part. Here it's a completely new need. Whereas with original design, right, everything is new. You're addressing a new need that nobody else has really addressed before. You're creating an original design to do it. It's a lot of work. It's a tremendous amount of work, and the amount of possibilities, right, are much greater. Right. So with adaptive design, you already know your solution for the most part. You're just changing it. Again, with redesign, you know your solution for the most part, you're just changing it. So your number of possibilities is far smaller than with the original design. And again, with selection design, your number of possibilities is even smaller. So as we move up, there's more complexity. And as you might expect, the type of jobs that you will get typically start at selection design. So I had a friend who got a job right out of college who his job was selection design, pure selection design. He bought things for the Army, right? So they told him what they needed, and he looked through manufacturers' catalogs to buy them, right? I had another friend who started with a medical device company making stents that would be fit into the blood vessels of your heart, right? To deal with heart attacks. And she did some very basic redesign. Barely changed the design at all, but I think changed the geometry in a small way to prevent fatigue at this one point, right? Very small amount of responsibility, really, right? When I got a job out of college, I worked at the job I got was at GE Aircraft Engines, and they told me right off the bat, they're like, look, you will not be doing what essentially was original design, designing new types of aircraft engines for at least 15 to 20 years working at GE Aircraft Engines. And the reason is because it's very difficult, and you need lots of experience generally, because it helps you narrow down the range of possible solutions because you already know what's going to work and what's not going to work. Great, so these are the different types of design, and you won't do redesign in this class for the most part, but you'll do adaptive design a lot, right? You'll take known solutions to other to problems that work, and you'll adapt them to fit towards your particular problem that you're going to be addressing in this class, your particular project. You'll do a lot of selection design. You do not want to make every single thing for this product that you're going to make, so you're going to select components from manufacturers' catalogs that meet your requirements that you're going to develop, right? And you may do some original design in this class, but it's very difficult, like I said, and takes a tremendous amount of time. So we will see. But you're welcome to give it a shot. All right, so let's talk a little bit in more detail about the basic steps of the design process, right? So the first thing we're going to do in this class, is we're going to identify a relevant need, right? Not a cool product, not something that not something that, not a product. We're talking about needs here, right? We're going to rigorously define the who. Who is going to be using this product? Not just the end user, but we're also talking about people who ship products, people who, the manufacturer, if you're selling it at a store, what are the store's requirements? These are all the who's. We're going to figure out what they need, what are their requirements, what their needs are, right? And then, as an engineer, and this is what I would say is your value added as an engineer. I hate that. You must translate these needs into what we call engineering requirements. Okay? So, a customer tells you that they want an energy efficient car, right? What does that mean in terms of energy? They just want to spend less on gas, right? Their need is to spend less on gas. As an engineer, right, we turn that into energy efficiency. What kind of energy efficiency, right? Energy efficiency is a requirement that we have, and then we can often set targets for these things. So we might say, look, we want this thing to be at 55 miles per hour to be, what's good for a car, maybe 20% efficient, right? So we're going to set these targets that actually use numbers, right? Because this is how we're going to evaluate our design as we go along, right? Spending less on gas, it's very difficult to evaluate a design using this kind of somewhat ambiguous language. So we're going to define energy efficiency and we're going to set these targets. Or maybe we're going to say, simply say that more efficient is better, right? Sometimes we'll do that. We don't have a target necessarily, we just say we want it to be as efficient as possible. Once we've developed a need and really spent a lot of time setting these engineering requirements, which use a lot of numbers, right? We want numbers. We're engineers. You didn't spend all that time learning math and doing all these problems for no reason. Once we've done that, we are going to start on conceptual design. Conceptual design. This, I don't know, if you ask me, this is the fun part. This is the part where you get to dream. We're going to do a broad search. This is a broad search of the solution, what we call the solution space, right? The range of possible solutions to our problem. And this is a good time to say that it's very important to not, at stage one, already have an idea of how you're going to solve this problem. This is something that I see happen over and over again in this class, is that you think of a problem and then you automatically think of a really cool solution, right? So what's something I see come up over and over again? Something I'll see come up over and over again is people want to redesign windshield wipers, right, for cars. And they'll have a really cool idea in mind. They'll say, look, we're going to blow hot air over the windshield of the car. It's going to be sweet, right? And then they develop their engineering requirements specifically for that solution. So they'll say, our design needs to blow air at a fast speed, right? So the speed of the air, the airspeed needs to be high, right? When the real need and the real requirement is to remove water, right, from the surface, to melt or remove, not even melt. Melting specifies something. We want to remove ice. Remove ice. These are the actual requirements. These are things that need to happen, whereas airspeed limits your design right off the bat, right? So we want to develop these needs and requirements without having any kind of conceptual design in mind, right? Then what we're going to do is, based on these engineering requirements that tell us what we need to do, we need to remove water, we need to remove ice, we're going to do a broad search of the solution space for concepts that do these things, right? This, like I said, is difficult. It's fun, but it's difficult because it requires intuition, right? You have to imagine these products working and how they would work, these solutions and how they would accomplish your goals. It requires some experience, right? The more you do this, the better you get at it. Simply because you've tried things and you know that they work or they don't work. It takes research. We're going to do in this class, we're going to do a benchmarking report where you look and you see what other people have tried to solve problems that are similar to this. And it's perfectly okay to, like I said, do adaptive. In fact, it's desirable to do adaptive redesign. You know this is an acceptable solution to one problem. Let's change it a little bit so it's perfect for our problem. So this is research. We're going to do rough calculations. If we can, back of the envelope calculations. Is this efficient enough? Is this going to be strong enough? To narrow down our range of possible solutions to just a handful. In this class, we're going to do a primary and secondary design, right? In real life, you would probably have 4 or 5 possible solutions. After this stage, so we've sketched out this design, and when I say sketched out, I mean literally sketched out. You guys are going to draw this out on sheets of paper. You're going to label the important parts, but for the most part, that's the level of detail we're looking at. You're going to start with, after that, once you've picked your primary design, you're going to start with embodiment design. Now we're going to increase the level of detail of our design, and with our goal is to, this is why it's called this, right? You're going to embody all the major requirements in your design. So all of our requirements that tell us what our product has to do, right? So melt ice, remove water. We're going to make sure that our product has some kind of feature that allows us to do each of those things, right? We're not going to worry right now about all the details of how it'll do that. So, for example, if we want to blow hot air over our windshield to melt the ice, we just have to make sure we have a heater of some kind, right, and a fan of some kind. We're not going to worry exactly about how we're going to heat the air. We're not going to worry about, in terms of like what kind of wattage we're going to use, right, for our heater. But we just want to make sure we have a heater there. So we're going to embody the major requirements in our design. It has to do everything we know it needs to do. Once we've done that, then we're going to start working on detail design. And again, like I said, this is an iterative process. Once you're going to start working on embodiment design, you're going to go, oh man, I really can't melt ice easily like as I thought. I'm going to have to go back and change some of my conceptual designs so that we can more easily melt ice, right? Maybe we need to add some kind of, instead of just blowing hot air like we thought our conceptual design would work, we're going to need to incorporate some kind of ice melting system, chemical ice melting system, so like antifreeze or something like that. Now with detail design, you're going to set, like I said, all of the details. You're going to set materials. You're going to set geometries. Oops. What are the geometries of your part? You're going to set manufacturing, right? So your manufacturing might dictate the geometries that you can use, the range of geometries that you can use. So manufacturing methods. You have to figure out how you're going to assemble this thing. At the end of this detailed design, and this requires detailed design requires you to do analytical calculations, right? And possibly simulations to ensure that your product can meet your meet your engineering requirements, right? These engineering requirements are the most important part of this entire class. If you do not have good engineering requirements, you will not have a good design, because obviously you won't know if you, at this point in your detailed design, you won't know if your design is good or not. So yeah, you're going to do analytical calculations. You're going to do simulations in order to make sure that the materials you chose, the geometries you chose, are going to be satisfactory. And finally, this stage is going to end in this class. It's going to end in fully specified and detailed drawings and assembly drawings. So you should be able to, at the end of this class, at the end of this semester, hand off a stack of drawings to some other group in this class, and they're going to make your product. Right? Those drawings need to be good enough that they can do that. All right. So finally, I want to talk a little bit about what makes a good design. And I want to stress this over and over again. What makes a good design? It meets our engineering requirements. And why do we have engineering requirements? The reason we have engineering requirements is because they are a concrete goalpost for us to aim for. You'll find if you don't do a good job with your engineering requirements, you'll sit forever just trying to figure out kind of ambiguously what's good, what's bad. You'll argue with your teammates. You won't have a clear way of making decisions, right? One thing you'll learn in this class is how to make these difficult decisions as a group, right? And I talked about earlier about how what's difficult about design is discipline, right? Well, part of that discipline that makes it easier are these engineering requirements. It's like if you're trying to diet, right? And you just say, I'm going to eat less. No, that's very difficult to do. It's much easier to say, I'm not going to eat, I don't know, what's something silly? Oranges. I'm not going to eat oranges. That's much easier to do than I'm going to eat less, right? All right, so meets our engineering requirements. What kind of engineering requirements can we have in this class? Well, one, we can have primary, what I call primary engineering requirements. These are the engineering requirements that are directly related to the purpose of our product. What will our product will do blank, right? This is what it will do. These are its functions, okay? These are very important. You need to nail these if you're going to have a successful design. Then there might not be a whole lot of these primary engineering requirements, but they're very important. It's far more common to have a large number of secondary, what I call secondary engineering requirements. So these are things like reliability, safety, aesthetics, how it looks, things like the total life cycle of your product, which are important, right? These are very important things. Like for the total life cycle, you want to worry about how it's going to fail, right? Failure mode. If you can, you want it to fail in a way that's not catastrophic. To go back to the bike example, it's not uncommon for frames to break. One of the nice things about a steel frame is that when a steel frame fails, it bends, right? And you can see that and get off your bike, and it's okay. You don't have a bike anymore, but you still have your face, right? One of the problems with a carbon frame bike is that when they fail, they shatter, right? They fracture. They completely break. So the front end of your bike will completely break off, and you'll go tumbling face first into the pavement. So how is your product going to fail, right? And in the case of carbon fiber bikes, by the way, yeah, the failure mode is worse, but one of the reasons that you use carbon fiber is because it's just so dang light, right? Failure mode, fatigue. You have to worry about fatigue if you're using metals, right? Interesting note, carbon fiber doesn't fatigue. Creep. If you're using plastics as a structural material in your product, under constant load, you have to worry about creep, things slowly deforming over time. You have to worry about corrosion, right? How will this thing deal with corrosion, elements, rust? Stability. Maintenance, and energy use, right? Efficiency. Surprising number of products. The major cost ends up being all of these total life cycle things, right? So it might be cheap at the beginning, but that water heater will cost you a lot more money in the end, right? If it uses a lot more energy. A big thing now, a huge thing now is end of life, right? How will your user dispose of your product? Will they have to spend money to dispose of it? Can they recycle it? An interesting thing about your lead acid battery in your car is that something like 96% of that battery is recycled. And they're built so that they can be easily recycled because that lead is actually fairly expensive. And if they can recycle it, well, one, you don't want to throw it away. Lead in the environment is terrible. But two, if you can recycle it, you can actually save a lot of money. So, end of life. Regulatory and what I call social issues, right? Regulatory and social issues. These are voluntary ones. Examples of voluntary regulatory agencies are ASME, ASTM, these professional societies. Interestingly enough, people talk about this all the time, but for example, if you're building a boiler, right, you're going to follow ASME's boiler guidelines when you're making this thing, just period. And the reason is because not the government requires you, but if it fails, right, you can point to these ASME requirements and say, I was building these to code. People have been building these to code for 100 years. I did everything right? But if you don't follow these requirements, you're much more liable to lose a lawsuit if your product fails. So some of these are voluntary, but everybody follows them. And actually, boiler requirements haven't been updated in a long time just because they'd be so darn expensive. No individual company wants to spend the money to find these new kind of requirements. So actually, everybody follows the same ones that were made a long time ago. We have government regulations. Government regulations. For good or for ill, we have a lot of these to worry about. We have OSHA, So when you're making your product, are you going to make it so that they can create it safely? We have the EPA. When your product's manufactured, its end of life, its use, will it conform to EPA regulations? We have the consumer. If you're making a consumer product, the Consumer Product Safety Commission, which has a big say in your actual product. The CPSC actually requires, this is fascinating, they require designers, well, they require the company then requires designers, but to foresee unintended uses for their product and prevent it. Or if you can't easily prevent it, right? Or you have to put a warning label. So good examples of warning labels are, because you couldn't really prevent it, flammable beds, right? Oops. Flammable beds. The largest, I think, not the largest, but at least the second or third largest recall in U.S. history was for those hanging blinds. If you look, every time you buy some blinds now for your window, the string that hangs down will have a warning tag on it that warns you about strangulation possibility. I think something like 25 to 50 million blinds were recalled in order to put those tags on them, because you can't really duplicate that functionality without having a hanging string, and a hanging string is going to possibly choke somebody no matter what you do. So you have to put a warning label on it. I love this story, but a fascinating story of somebody getting sued for not foreseeing unintended uses is a man was backing an ATV down a hill, right? So we have a hill. There's a guy on an ATV. Here's two wheels. I should not have tried to draw this, but whatever. So here's our ATV. Here's our handlebar. Here's our guy. He's standing on it. Handlebar, face, yeah. So he's backing it down this hill, and his foot slips and hits this rear fender right here, right? His foot slips, hits the rear fender collapses, his foot gets trapped between the fender and the wheel, and it pulls him through, which way is the wheel going? Through and around the wheel and underneath the ATV, right? So he sustained a tremendous number of injuries. His leg got messed up pretty bad. And he sued the company, and the company who made this was Yamaha, actually. Yeah, Yamaha. Yamaha made this ATV, and he sued them. Interesting fact, when he was doing this, which he was backing an ATV down a hill, I don't know why you would ever do that, but he did. He was, currently taking Oxycontin. And it was legit. He was on it as a part of a prescription, but that slows down your reflexes, right? 2, even worse, he was within 75% of the legal limit for alcohol consumption for driving a car, but still. So he was clearly somewhat impaired, probably by the interaction of Oxycontin and some alcohol. He was not only using the ATV incorrectly, but he was also impaired in terms of his ability to drive this thing, perhaps physically impaired too. And yet, the courts found that it was Yamaha's fault. Why? Because they should have designed that rear fender so that it doesn't matter why somebody did it, but if their foot hit that fender, it would not collapse and not drag him underneath the ATV, right? So it doesn't matter the situations under which the user misused your product, but if it's a reasonable chance that that would happen, you have to design for it. So that's designing for safety and that kind of stuff, right? All right. Next class, I think we're going to start talking about defining our problem.